In this video, I'm going to go over predicting products. Now, I do not use the activity series, which is the one you would use to see if a single displacement reaction occurs, and I am not using the solubility chart. I will make a different video for those two. This one is going to be about classifying reaction types, predicting the products, and then balancing the equations. So we start off with this first one. You have these two elements that are being added to each other. There's really only one option for what that could be, is synthesis. When you have a synthesis reaction, you are going to get one product. So now when we look at this, we have barium being added to oxygen. When we have that, that's going to form an ionic compound. So what you have to do is look at the oxidation numbers. Barium is +2 off the periodic table, oxygen is -2. So those charges cancel out, and what you're left with is BaO. Now, a common mistake that people make is they see a 2 here on oxygen. The reason why this oxygen has that 2 is because oxygen is diatomic. That 2 is not necessarily going to come over to the product side. What you have to do is to figure out this formula. In this case, you have to look at the oxidation numbers. Once you figure out the oxidation numbers and you have the formula, you do not change this formula. You don't add a 2 here to get the oxygens to be balanced. What you do is add coefficients. So you change how much you have of that compound. You don't change what the actual compound is. So now there's 2 oxygens on the reactant side, so I have to put a 2 in front of the barium oxide. Now that changes the amount of barium. So we put a 2 in front of barium on the reactant side to balance it. So remember, just because there's a 2 on the reactant side does not mean you put a 2 there. You have to figure out the charges in this case. Now the next reaction, you have a single element being added to a compound, and what's going to happen is this zinc is going to go in and replace that copper. This ends up being a single displacement. You can also say it's single replacement. It's really saying the same thing. Now zinc, when it's by itself, it does not have an oxidation number. The way these elements get oxidation numbers is by either gaining or losing electrons. And at this point, it's not doing either of those, so it does not have an oxidation number. But when it starts to kick out this copper, it's replacing the copper, now it's going to be bonded to the sulfate. So now what we have to do is look at oxidation numbers. Zinc is a +2, sulfate is a -2. So again, those 2's cancel out. What you end up with is ZnSO4, zinc sulfate. And now copper is by itself. Now don't get confused. If you look at the periodic table, copper can have either a +1 or +2 oxidation number. But at this point, it's forming a precipitate. It's dropping out of solution. It's not bonded to anything anymore. And it is not diatomic. So we would just write it as Cu. Now you look at this, everything is balanced. So we're good how it is. We don't have to add any coefficients. Now for this one, it's barium chloride reacting with sodium phosphate. You have 2 compounds that are being added to each other. That's going to be a double displacement. They're ionic compounds, and they're going to switch their partners. But when they switch, remember you have to pay attention to oxidation numbers. Barium off the periodic table is +2. Chlorine is -1. Sodium is an alkali metal, so that is +1. And phosphate is -3. Now, when these things form ions and they break apart, with the way the reaction occurs is the positive from one compound, so this cation is going to react with the anion from the other compound. So the barium and the phosphate are going to bond together. But what happens here, you have to pay attention to the oxidation numbers. This 3 from the phosphate is going to become a subscript for the barium. Now we have to put the phosphate in parentheses because this 2 from the barium is now going to be a subscript for the phosphate. So you get Ba3, PO4 in parentheses, and the 2. And now you have sodium that's going to bond to chlorine. It's a +1 and a -1, so you get NaCl. Now again, notice, I did not carry over these subscripts like this 3 for Na3 does not show up over here. The whole reason why it has a 3 here is because sodium's +1 and phosphate's -3. So when you crisscross those numbers, you get Na3PO4. That's how this ionic compound ends up neutral. Because now you have 3 sodiums, they're all +1, so that's giving you a total of +3, and the phosphate is -3, and they cancel each other out. Well, that's the idea of what we're doing over here. We want to make sure these compounds are electrically neutral when we balance them. I'm going to clean this up a little bit. All right, so always get the oxidation numbers to figure out what the compounds will be. Now, once we have those formula written out, we are not changing those subscripts. What you do is you add coefficients to balance it. And there's different ways you can do this. You can start with different things. I'll just start with barium. I have 3 bariums on the product side, so I'm going to put a 3 in front of barium chloride. Now that gives me 6 chlorine. And over here on the product side, I only have 1, so I have to put a 6 in front of NaCl. Now that gives me 6 sodium, so I have to put a 2 in front of sodium phosphate to give me 6. Now the good thing is that gave me 2 phosphates, and here I have 2 phosphates. So that one's balanced. Alright, I'm going to scroll up. Alright, number 4 is a very specific type of reaction. A lot of times people look at this and they might think it's a single displacement because you have an element being added to a compound. But what happens is you have a hydrocarbon, which is carbon and hydrogen and sometimes oxygen, and it's being reacted with O2. This is a combustion reaction. Once you realize it's a combustion reaction, you can write the products down right away. Combustion reaction always have the products of carbon dioxide and H2O, no matter what. And so we didn't have to look at oxidation numbers or anything like that. Once you see a hydrocarbon and O2, you're going to get CO2 and H2O, and it doesn't matter which order you put those products in. As long as they're on the product side, that's good enough. So now we have to balance this. 6 carbons on the reactant side, so 6 carbons on the product side. 12 H's on the left, so we need to get 12 H's on the right. So remember, you multiply the coefficients of the subscripts, that gives you 12 H's. Now the oxygens we have to pay attention to because they're in everything. You have 12 oxygens here, plus another 6 is giving you 18. But when you're balancing this, remember, you have these 6 oxygens here, plus these 2. So what I'm going to do is take these 18 from the product side, and I'm going to subtract out this 6. Because if I can, I'd really like to balance it just with this O2. I'd rather not have to put numbers in front of this C6H12O6, because if I put numbers in front of that, it's going to change what I did over here on the product side, and then I just have to start all over. So I have 18 oxygens on the right. Subtract out those 6, that means I have 12 left, and I can balance that with O2 by putting a 6 in front of it. So now double check our work. We have 6 carbon, 12 hydrogen, 12 hydrogen. You have 6 oxygens plus 12 is 18. Here you have 12 plus another 6 oxygens, so that one's good. Alright, number 5. You have an element being added to a compound, and this zinc is going to come in and take the place of that lead. So this is going to be a single replacement or single displacement. Remember, you could use either wording there. They mean the same thing. When you do this, you have to pay attention to the charges. Again, zinc, when it forms a bond, is going to have a positive 2 charge. And it's going to bond to the anion from the other compound, which is nitrate, NO3, which is -1. So what you end up doing is getting Zn NO3 in parentheses with a 2 outside. That is zinc nitrate. And now, again, like we did with the other single displacement, lead can have different oxidation numbers, but it's precipitating out. It's not bonded to anything, and it is not diatomic, so it's just Pb. Alright, so now we want to balance this, and let me move this up a little bit. Alright, so we have 1 zinc on the left, 1 zinc on the right, 1 lead on the left, 1 lead on the right. We have 2 nitrates, and here we have 2 nitrates, so that one is balanced how it is. Okay, number 6. There's only one thing to the left of the arrow, so we only have one possibility there. It's going to be a decomposition. That thing is unstable, and it is decomposing. Sometimes you have to heat them. Sometimes they might happen on their own. It depends on the compound. But it's decomposition. Now, if it's decomposition at the 5.0 level, I have to give you some kind of hint as to what the products are. If you're taking honors or a higher level class, you might be required to know what's going on with that. But for this one, I'm giving you a hint. You have potassium chlorate. Potassium chloride is one of the products. So the only thing that's left over is oxygen. But remember, oxygen is diatomic. So we have to write it as 2. You don't want to just say, okay, well, there's 3 oxygens, so I'm going to make this a 3, and it's all going to be balanced, and everything's going to work out. What happens is it's diatomic, so you write it as O2. So now we have to balance it. The potassium and the chlorines are good. It's the oxygens that are off. So remember, if you have a 3 on one side and a 2 on the other, the easiest way to balance that is, well, if this is a 3 on the reactant side, make the 3 a coefficient on the product side. Since that's a 2, make that a 2. So now on both sides you have 6 oxygens. And we've finished off with the potassium and the chlorine. Alright, number 7, hydrocarbon and oxygen. Alright, again, it's not single displacement, even though it's an element being added to a compound. This one is going to be combustion. Combustion, once you realize it's combustion, write down the products. No need to look at oxidation numbers or anything. You're always going to get carbon dioxide and water. So now we can balance it. 4 carbons, 8 hydrogens, so we need to have 8 hydrogens on the product side. Now count the oxygens. You have 8 plus another 4. So what you can do to balance that is put 6O2, and then everything is equal at that point. Now number 8, it looks like a double displacement. You have these 2 ionic compounds that are being added to each other, and it's going to behave like a double displacement. But what happens is H2SO4, that is sulfuric acid, and NH4OH is ammonium hydroxide. So you have a strong acid and a weak base. This ends up being an acid-base reaction. Right? An acid-base reaction you can think of as being a specific type of double displacement reaction. So when we do this, we have to pay attention to oxidation numbers. Because these things are going to form ions, and when they go through the reaction, the cation from one is going to bond to the anion from the other. So we could start off with this ammonium, for example. That is NH4, that's a positive 1. It is going to bond to the negative on the other side. So what you get is ammonium sulfate, but pay attention to those oxidation numbers. Since sulfate has a negative 2, we have to put a 2 with this ammonium. And now we can write SO4. Since ammonium's a 1, you don't actually have to write a 1 here. Now, one of the good things about acid-base for us at the 5O level, what we're doing is acids for us are always going to begin with H, and at this point we're going to say they always end in OH. So what's going to happen at this point is you're always going to have this hydrogen bonding to a hydroxide. So what you get is HOH, which you can write as H2O. So now we have to balance this thing. Okay, so first thing that jumps out at me is I have 2 ammonia on the product side. So I want to get 2 ammonium ions on the reactant side. Now, that gives me 2 hydroxides. And if you want to, and you don't have to do it this way, but if you want to, you can balance the H2O, if you want to think about it as HOH. Because what I can do now is balance the 2 hydroxides with these hydroxides on the bottom. So I'm going to put a 2 there to give me 2 hydroxide. Now what that does is change the hydrogen. And if I want to, I can balance the hydrogen with these hydrogens on the left. So you can see I have 2 hydrogens, and here I have 2 hydrogens. Now you don't have to do it that way. You can balance it by the H2O, written as H2O, and that would be fine. But we can double check our work. We have 2 hydrogens and 2 hydrogens, 1 sulfate group, 1 sulfate group, 2 ammonium, 2 ammonium, 2 hydroxide, and 2 hydroxide. Now let's say you looked at it as H2O and you didn't do this part. You just still get the same idea. You have 2 hydrogens here plus another 2 hydrogens, and that's giving you, well, this coefficient goes there, giving you 4 hydrogens. You have 1 sulfur, 1 sulfur. You have 4 oxygens here plus another 2. Here you have 4 oxygens plus another 2. You have the ammonium phosphate, the ammonium polyatomic ion. And then everything else is accounted for. Right, Alright, so that is balanced. So remember, you want to classify the reaction type first, predict the products, and you may have to look at oxidation numbers like we did for that last